Welcome everyone to our first exclusive webinar for Pdisp. I'm hoping by the end of today or this session you'll have a very good understanding of how Pdisp works, and hopefully you can go into it with confidence. So really the objectives of today are a brief presentation covering the basics of Pdisp, the analysis methodology, a quick discussion of the two methods and which should be used, a case study showing how reliable Pdisp can be. But the main bulk of the presentation today is the live demonstration. So I'm going to carry out a basic settlement analysis and show you how to do it. We're going to be using graphical inputs as well to set up a very quick analysis. I'm going to introduce to you some useful shortcuts and tips to enable you to model very proficiently, very quickly. And also, one of the big strengths of Pdisp is its graphical outputs. So I'll show you what kind of graphs are available, how to produce them, and also the tabular outputs. What are they used for? How do you export tabular outputs? How do you do further analysis? So I'll introduce you to those many things today. So it's quite a long demonstration. Unfortunately, we're cut for time, so I won't be able to cover some features such as GSA raft and soil structure interaction. And also, if you want other tutorials on setting up Pdisp, you can refer to our website and I'll show you at the end of the presentation how to do that. So to start with, I'll give you a quick introduction into Pdisp. Pdisp is effectively soil displacements due to pressure. So it calculates displacements due to the application of a pressure, and this pressure could be either loading, such as any kind of surcharging, which is shown on this image here, or unloading. So for example, if you've got any kind of demolition, then you can analyze that using Pdisp, and we'll be carrying out examples of both. It's also quite good for flexible footings or rafts, because if the footing is flexible enough that it moves with the soil, then you could really analyze it very simply using Pdisp, which is an elastic analysis. If you do have any kind of stiffnesses, then you should be looking at GSA raft. So the two analysis methods which are available are the Boussinesque, which gives stresses and displacements in the soil. It's also able to deal with non-linear soils, so it's very good in that way. But the Mindlin method is an elastic analysis. It gives displacements only, but it can deal with shear, and it also gives horizontal displacements. So, for example, if you feel that your soil is pressing down and out, the Mindlin would be a good method to be using. Now, if I compare the two methods, they give vertical displacements and vertical pressures. But if you're interested in the horizontal displacements or traction forces, you should be looking at the Mindlin method. It's also theoretically exact for a homogeneous soil. For the Boussinesque method, it's very good to deal with soil nonlinearity. And if you want to calculate stresses, then you should be using the Boussinesque method. In terms of choosing an analysis method, there are some caveats. When you do decide to choose one or the other, you should be careful in how you set up your model, because it affects the results sometimes. A lot of detail is given in the manual for this and in our new step-by-step guide, but I'm just going to touch upon it now. So for the Boussinesque method, if, for example, you've got a stratum of, say, 10 meters in depth, and you say that you want the computer or want the program to only calculate the displacement at the top and the bottom, that may not be very accurate. So you need to put more displacement levels in to the file or to the analysis, so that it can the computer or the program will calculate displacements at different levels, and it makes the Boussinesque method more accurate. In terms of considerations, if you've got varying Poisson's ratio, this impacts on your global Poisson's ratio, so you should be careful in how you choose it. And if there are sudden changes in stress between soil strata, be aware of this and its effect on accuracies, and put displacement levels in accordingly. But you would have to read about this in a little bit more detail. With the Mindlin methods, it's very good in terms of it gives horizontal ground movements, and it does consider settlements above loads, which the Boussinesque doesn't do. But just be aware of its limitations as well, and have a look in the manual for that. With regards to the Pdisp input, if you look at how you input into Pdisp, you can really understand how to set up the file and how the analysis works. So you need to input the actual loads, which are rectangles or circles. You need to also put in the soil profile. So the soil profile is a set of stratigraphy, and in many cases, for example, you could have a fault, you could have a soil lens. So for those kind of cases, you would put in different soil zones. Say, for example, your strata is not necessarily horizontal. Soil zones would be a good way to model that. You also need to define your rigid boundary, which is the point of rock, which is at the bottom. So once you put your loads and your soil data on, remembering that it's elastic analysis, so your soil data is mainly the Young's modulus and Poisson's ratio, you also need to tell the computer where you want the settlements calculated. So that's what the displacement lines, points, and grids are, and you need to put that in accordingly. You also need to specify your analysis method. So are you going for the Minden or the Boussinesq? In terms of shortcuts, there are a number of shortcuts available in all the geotechnical programs. This is one of them. For example, you can put defaults in these grey boxes, which are shown here. Once you put your default in, instead of having to type in every time load, horizontal, 0, if you tab through these boxes, it comes in automatically. And you can change your defaults as well in the grey box. So that's quite a useful thing. Also, if you're putting together a number of tables, you can use the equals or the equals buttons to either copy a cell or copy a line from above. If you've got a very long table, so say, for example, you've got a number of displacement points and lines, then you can use Control-G and type the line to go into. Also, another feature is that if you right-click, you bring up a whole list of options. So say, for example, you wanted to do a sensitivity check. So you wanted to add a certain number to all your Young's modulus or factor it by a certain amount. Then you could do so by using modifiers and instead of typing it in to everyone. Here's just an outline of the soil profiles really, and it shows that you can vary the Young's modulus. It doesn't have to be a consistent Young's modulus, and it shows how the different zones work in 3D. In terms of putting your zones in plan, your largest number overrides the smaller number. So as you can see here, instead of having a simple square grid configuration, we've actually got something more complex by putting zone 3 over zone 2 and zone 1. So if you do have more complex soil stratigraphies, or for example, say you've got a lens in the middle, then you can model it, and then there's no reason you can't do that. Also, we've got horizontal and tangential loading. So especially for the Minden method, this is extremely useful. You don't need to have loading based at the horizontal. It can be tangential, and displacements will be calculated accordingly. In terms of the output, I think this is one of the strong features of Pdisp, because you've got a number of attractive outputs which are good to put in reports. So the graphical outputs, for example, you can just plot contours and plan. You can plot contours or plot deflected grids in 3D and show that in relation to your loads itself. And for example, you could pick a point, say you were interested in what's happening right at the center, and print out a soil column displacement chart. And this gives you the displacement at different levels and shows where the bulk of your displacement is occurring. So it really does help you understand better how the soil is behaving and how your stiffnesses are impacting on settlement. So I'm just going to touch upon a very quick case study. Unfortunately, as Pdisp often deals with settlement, a lot of the case studies that we have received are confidential, and this one is no different. So this is a case study from Arab. Arab was responsible for designing a building in London directly above some LUL tunnels. A 3D FE analysis was used to model the building and the piles because the movements in settlements were extremely sensitive, and the client was very concerned about settlements in this case. But the Category 2 check was necessary, and this was undertaken using Oasys Pdisp. So this is quite a nice case study because it compares Pdisp to 3D FE. So this is just an example of the kind of graphical outputs we get. So as you can see, you've got your deflected grid here. You've also got your deflected lines. So these lines are along the crown of the tunnel. And as you can see, you've got displacements occurring along the tunnel here. So if we look at the stresses first, LS Dyna, the 3D FE program, calculated stresses shown here. We've got a maximum stress of 68 kPa occurring here, where you've got this blue patch here. And for the 3D for the Pdisp analysis, you can see that we've got a similar pattern of movement. So the maximum displacement is actually occurring at the same point. And also, if you look at the stresses and the maximum stress here, the stress is 68 kPa, and which is exactly the same as the 3D-FE analysis. So that's very comforting to know, and quite a good result. But further to that, how do settlements compare? So we've had a look at stresses. Now, when we go into settlements, the peak vertical ground movement for the 3D-FE analysis was 3.18 mil, and this is compared to 6 mil in Pdisp. So Pdisp is more conservative. And the reason for this is that if you model in 3D, you're modeling structural stiffnesses of the foundations, tunnels, and walls. And you don't get this necessarily in Pdisp unless you combine it with a program like GSA, for example. So that's why you get a more conservative result, but for a lot of cases, this is actually a very good result. And you can see also the trends of movements are similar. So the peak settlement is occurring in the same place for the 3D-FE analysis and for the Pdisp analysis. So we've covered our case study. In terms of developments, we're constantly developing our software. We've got new versions of Pdisp coming out regularly. Recently, we've added the horizontal displacements and forces. We've also introduced the GSA raft analysis. So those are recent developments. We have also added a new feature which combines the movements from Pdisp, which is our program that calculates ground movements due to excavations, and Pdisp. Now, this gives us a very powerful program. It's an all-encompassing 3D program. So, for example, if I had some kind of loading happening here, or maybe I'm demolishing a building, and along here, at the same time, we're building a tunnel, or say, for example, we're putting a basement excavation in there, I could actually combine the two programs and get the overall displacement due to the excavation and due to the loading of the soil. So it's an excellent way to model things in 3D. And further to that, one of our customers recently did an analysis of how, of time saving and cost savings in terms of Pdisp and FE. So, for example, if you look at this, Pdisp is much quicker in terms of, for example, setting up the model and running the analysis and even interpreting the results than 2D-FE and 3D-FE, such that Pdisp and Pdisp would take around 1.5 days compared to almost half a month for 3D-FE. So that's why a program like Pdisp and Pdisp is actually quite powerful. So having run through what Pdisp is, its strengths and features, and a good case study, I'm now going to go into the program and show you how to run a quick analysis, and hopefully this will help you be very proficient at modeling. Okay, so starting Pdisp, we set up a new file. We look into, say, for example, giving it a job title. So this is just loaded soil. And you can give details of the calculation. For example, say you're doing a number of stages or various other things. That's all available here, and that shows in your printouts of your tabular and graphical outputs. In terms of the analysis option, we are choosing the Boussinesq method. Generally, the Poisson's ratio of our soils is 0.25. We've got a horizontal rigid boundary at -30. Okay, so I'll apply this. And if I go into my PowerPoint presentation, you'll see, for example, that our rock here for this particular problem is at -30. And we've got a number of soil profiles here, and we've got a number of soil zones. So we need to now input the soil profiles in soil zones. So I'll start with the soil profiles. Okay, so for soil profile 1, the level at the top is 0 meters OD. We've got a number of intermediate displacement levels. So this tells you how many times that how many levels the program will be calculating at. And I'm going to put 21 here. Young's modulus 20,000. It's a constant Young's modulus, so 20,000 at the bottom as well. Poisson's ratio of 0.25. And the color, you can change it if you wish. So level at the top is -10, 21. So what we've done here is this strata is 10 meters thick. And by setting 21 intermediate displacement levels, what that means is that I have 20 intervals in the soil, which means that I'm basically having a displacement calculation every 0.5 meters. So you can change that accordingly. For example, if you have significant changes in stresses between soils, then you should probably increase this. If you feel that there's not much change, then you could decrease it. Okay. So I'm just going to press the equals button here because it's the same value. Tab it through. So that's another shortcut. Equals again because it's the same value. And there you go. So that's soil profile 1. For soil profile 2, a good feature of Pdisp is copying and pasting. So for example, say you know that you're using a certain type of soil regularly or various other things, you could actually have it in an Excel file and copy and paste through. Or for example, say you're setting up this file many times for different types of analysis, then having things in Excel or either copying and pasting between Pdisp files is quite a handy tool to have. So I've put my 2 soil profiles in. I also now need to input my soil zones. So if I look at, if I go back to the Pdisp analysis, I've got 2 soil profiles and they go into soil zone 1 and soil zone 2. Okay, so as you can see, we've go from -100 to 100, and then to 0 to 100. So the x values are changing and the y values are staying constant. So if I go into this, soil zones, I'm going to tab through soil zone 1. Okay, the minimum x coordinate is -100, maximum is 0. Soil profile 1. And then I'm going to tab to soil zone 2. X goes from 0 this time to 100. The y values are the same, so I'm going to use my equals button and soil profile 2. Okay. So I've now got my soil details in. I need to put my load data in. So if I go into my PowerPoint presentation, you can see that we've got different loads here. Load 1 is at 0 meters OD. It's a square. We've got this circular load here, which is acting at -1 meters OD. And we've got this rectangular load here, which is acting at -2 meters OD. So I've actually got this already. I put it into Excel file. I'm going to copy this and paste it through. And I'm just going to run through this with you. So for example, the orientation of all of these is horizontal. We've got 2 rectangular loads and a circular load. For that circular load, we have to break it up into a number of rectangles. So I broke it up into 7 rectangles, but if you wanted something very accurate, or say for example you've got a very large circle, you could break it up into more rectangles, but this would increase the length of time it would take to analyze. So if I go into my graphical input, I've got my loads and I've got my soil, but the Pdisp output would produce very little because you haven't yet told it where you want calculations of settlement. So there are no displacement points, lines, or grids. So this is where displacement data comes in. So if I go into my PowerPoint presentation, the displacement data we're going to put in are 2 lines. They could represent a utility or they could represent something of interest. These are going along the surface of the ground. I've got 2 grids. So one grid is at 0 meters OD and one grid is at -3 meters OD. But if you notice here, we've got a grid. And this grid is shown by this big green line. And I've split this grid up into 10 intervals. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 intervals along here. And the reason I've done this is because I want displacements to be calculated within these squares. So for example, because of the number of intervals I've chosen, displacements will be calculated along these points. Now say for example I just chose 3 intervals, then the displacements might not show for inside this loaded area, and you wouldn't get a very accurate looking grid, and the contours plotted wouldn't be very representative. So it is important that you choose the right number of intervals to lie within your specific loaded area, which is what we've done here. Okay, so now we're going to set up a grid. We'll call it grid 1. We're going to plot it in the global Y. Okay, and I'm going to go into the PowerPoint presentation to show you what this means. So if you're plotting the global y, what that means is that you've got a line here, and it moves up in the y direction. Okay, so this line, this red line, extrudes 170 meters out in the y direction. So you need to define this line. You need to define the depth it extrudes to, which is 170, and then you need to stipulate the number of intervals along. So that's how you define a grid. Okay, so if I go into Pdisp, I'm going to firstly define the first and last point of that line. So the first point is at -80, -90, and 0. And the second point of that line is at 80. The y point is the same because it's a line along the y, and 0. Okay, the number of intervals I'm going to take as 10. The extrusion depth, and if you remember, that was the depth of the y line going up was 170. Okay, number of intervals 10. I do want all the points calculated and shown in the tabular outputs, but there's no need to show the detailed results. So not showing the detailed results saves a little bit on analysis time, but it is important you calculate it, otherwise you won't be able to plot contours and various other things. So if I use equal equals here, I copy this grid across, and this time as I want to put it at -3 meters OD, so I just point the Z level at -3. I've got my two grids. Excellent. I've also want to put my lines in. So if I go into here, I've already put the information in there to save some time. Excellent. So we now have everything we need to run the analysis. So I'm just going to run, proceed. And as you can see, there's a little bit of difference here between the Boussinesq method and the Mindlin method. So although we've stipulated the Boussinesq, sometimes it's important to understand the differences and have a look at that. So for example, here we've got, it's only a small difference. It's about, what, 3 or 4 mil. But it's interesting to see where it occurs. So for example, we've got 4.5 mil difference. It's occurring at 0 meters OD, and it's occurring at -16, -39. So -16, -39 is around here. And as you can see, that's where the rectangle has come in. And as you can see, it's basically at the point where there are two loads, the circular load and the rectangular load, which lie underneath the soil level, the top of the soil level. So what's happened here is that the Mindlin method has taken account of settlements above these loads, but the Boussinesq method hasn't, and that's why there's a big difference between, well, there's a little bit of a difference between the two. So if I select all, I'll start with the tabular outputs. Pdisp produces a number of useful tabular outputs. As you can say, we stipulated to get displacements at the center of the loads, and that's what we've got here. We've got displacements along the different points of the grid, and the different points stipulated in the line and the final point. These tabular outputs often it's useful to analyze it further or do a more detailed analysis. So you can actually export the tabular output into CSV. Okay, so if I open this up, as you can see, we've got our tabular outputs here. So if you want to do further analysis, the program allows you to do so. We've also, for example, got options in terms of graphical output. So I'm going to start with the plan. One very useful feature is that you can actually plot line graphs for displacement. So for example, so you can see I've stipulated a number of points along the line, and this is calculated displacements for me. If I wanted this line to be smoother, what I could do is I could go into displacement data and increase the number of intervals. So if I increase this to say 20, and now did the analysis, if I now go in and plot the line graph, you'll see you get a much smoother line graph. So as you can see, this is helping you understand a little bit about how displacement levels or intervals work. So if I go back into the plan, I can also plot the contours. So as you can see here, I've got a number of contours shown in terms of line, or I can have the fill contours. I can also go between grids. So this is the grid 2 at -3 meters and 0 meters OD. So there are a number of options for contour plotting, and as you can see, there is a little bit of a difference because of the different soil profiles, which you can see here. If I wanted to, I could also annotate. So I can add an annotation in here if I so wanted. And zoom out of that. And in terms of further options, 3D graphics view is quite useful. So as you can see here, this is a very simplistic representation just of the soil zones and stratigraphy. But if I right click and go to Settings Wizard, I can click on Wireframe Display. And now I can see a little bit of the loads and the grids. In terms of the displacement grid, I can look at the deflected shape. So I can see how this grid has displaced in terms of the loads. Or maybe I can choose in some contours and say I can change a contour interval. So say I want to change it to 30. So you can see I've got the contour interval here. I'm looking at the displaced line, settlements along the line, and I'm also looking at the contours. If I wanted to say increase the number of contours or the interval, say to 5. Now I can have a look at the contours in that way. So there are a number of options available, and for a much more complex file, this really helps you understand where settlements are occurring and how they occur. You can zoom in and zoom out either using your mouse, and you can click from the wizard from here as well. In terms of the cross-sectional view, you can have a quick look at how your loads are acting in terms of your soils, and as you can see, some of our loads are acting below the ground surface, and that's why we have a difference between the Midland and Buzinesque. And I did mention soil column displacement. So say in plan, I was interested in what's happening right at the center, and I was interested to see where the maximum displacement is occurring. If I look at the soil column displacement, I can see what's happening there. So I can look at the displacements along the different soils. And as you can see, there's less displacement at the top because at that point we don't have some of the loads acting. Okay, so hopefully that gives you a good understanding of how Pdisp works, setting up a very simple problem and making use of your outputs. In terms of printing, say for example I was interested in printing this, I do actually get options here to, for example, put your company logo in, and we do get options. For example, if I had put details in the titles, I could have put information in here. In terms of changing the company logo, you go to Tools and Preferences to do that, and you put company info in. So hopefully that's given you a really good grasp of how Pdisp works and its strengths. If I go into the presentation, I do have another example for you, and this is a building demolition analysis. And you must be thinking, well, this is going to take a long time to produce, but I've got a quick workaround to show you now that hopefully you can appreciate and use. So this is a very simplistic example, but say we had a building 25 meters by 20 meters. We've got a few column loads here, and say we were going to demolish this building, but it's going to be demolished and it overlies an underground tunnel. Say this tunnel is 3 meters below ground level. How do you deal with this? Well, in terms of the pressures, these actual negative pressures, you can model this in Pdisp and you can model the tunnel. And I'm going to show you how to do so very quickly and very easily using Pdisp. I'm going to start a brand new analysis. Again, this time we're going to call it Demolition. In terms of the analysis options, this time I'm going to try with the Midland. We do calculate horizontal displacements. We're not going to use the legacy. Midland legacy is an older version of the Midland, and we find that the newer version can be a little bit more accurate. So only if you're looking retrospectively at an old analysis would you use this. The heave correction factor is incorporated automatically into the new Midland analysis. We're interested in horizontal loads on the horizontal planes. The rigid boundary in this case is at -8 meters OD, so it's where rock is occurring. I apply all these things. In terms of the soil profiles, I'm going to do a little bit of copying and pasting here. So we've got soil profile 1. and soil profile 2. Okay, so I've got 2 soil profiles in there. Now, instead of having to type everything else in, I'm going to show you a very useful shortcut. And I'm going to add this bitmap in, which the bitmap is actually a scale drawing of the problem that I've specified. And if you remember, it's 25 meters across, so I'm going to put the dimensions in accordingly in the x and the y, and 20 meters in the y, so it's minus 10, 10. Okay, so I now have a scale drawing of this particular analysis. It doesn't need to be a drawn one. Maybe you've got a bitmap of a CAD or a CAD drawing or something like that, so anything can be put in. So I'm going to use the graphical input feature here to put all my loads in, to put my displacement lines and grids in, and to put my soil zones in. So I'm going to start with the 2 soil zones. So here I've got profile soil zone 1 and soil zone 2. Okay, in terms of my loads, I'm just going to literally draw the loads in and type it as I go along. The loads are occurring at, I'm just going to check my soil zones and see, because what I had done with the soil profiles here is put a meters OD and not a ground level. So loads will be occurring at 10 meters. So if I go and put this in, the load is at 10 and the pressure is minus 150. So this load is at 10 and minus 100. So as you can see, it's so much quicker, and it's a very good way of approximating settlements. So if you want to do a very quick analysis, you could do so. Okay. 10, 50. So while I'm discussing this, it is worth noting that all of this is available in our new step-by-step guide. So this whole example file is available in the new step-by-step guide, and you can go through it and try it out yourselves. There will also be a recording available of this presentation, so that will be sent to you in due course. Okay, so in terms of displacement data, I can actually put the displacement line in very simply. So I've got this line here, and I'm going to say it follows along. Say this line follows along this tunnel here. If you remember, I said it was occurring at minus 3 meters below ground level. So in that case, that'll be 7 meters OD. We want a number of intervals across. Those intervals should be less than the distance between these loads to give a kind of accurate feel for it. So say in that case, we've got something which is about 20 meters long, say 40. So as you can see, there are a number of displacement points between this here. And again, for the grid, we're going to put a displacement grid in at the surface level. So that's at 10 meters OD. We want a number of calculation points. So again, I think, every half meter, so 40 should be around right. So as you can see, again, we've got points within the load. So we should show settlements reasonably well on our grid. So if I run the analysis on this, as you can see, we've got a number of points on the grid, so it took a little bit longer to run. So that's something that you should be aware of for very complex files, and maybe you should be taking smaller grids in areas of particular interest if that's the case. Okay, so run the analysis. I've got the tabular output as usual. If I look at this in plan, I can get the contours out. Exactly what you would expect. As you can see, settlement's a little bit more significant for one side to another side. We can have a look if we wanted at the line graph. So if I switch this off and click on this line, I can have a look at the settlements along. As you can see, it's heaved, so it's settling upwards. I can have a look at the settlement along the tunnel and see, for example, if I wanted to plot the actual gradient over here, that I could do so if I wanted to. There are also options available in the line graph, and you should be aware of this. So if you decide, for example, to right click, you can actually change the way your cursor shows. You can change the curve itself, you can export it, you can change the line weight, you can actually print this out as a JPEG. So within the line graph option, there are a number of options available. If I go to the 3D graphics view, if I play around with the settings wizard, I can go to the wireframe display. I can look at the deflected shape, for example. And as you can see, this is pretty much what we'd expect. You might also notice that there are horizontal movements. You can see that it's pushing out a little bit. And that's because we've used the Mindlin method here. So I can actually, if I look at the displacements here, I can maybe plot the global Y alone. And as you can see, we can look at how things are pushing out, which you wouldn't necessarily get with a Boussinesque. Okay, so I've covered quite a lot, and I've covered it quite quickly. But hopefully you get an idea of how efficient a tool Pdisp can be and how quickly it can calculate quite complex problems. So what next? Well, there will be a recording made available of this, but there is a step-by-step example which effectively covers the same examples and more. And I suggest you have a look through that and the manual itself. Our website provides you with all this and technical FAQs. So if you go onto the product page, which I can do now. So if I go onto the product page and say, for example, I click on Pdisp, I can have a look at information about Pdisp. The FAQs are here. User manual tutorials are available. We have our new step-by-step guide, so you could download it and have a quick look at it. And if I scroll through it, you'll see that actually it covers very similar problems to what we've been dealing with. But it does cover more examples like nonlinear soils and more detail about the actual methodology itself. If you wanted to, you can go into our YouTube page, check out our tutorials and also previous webinars on Pdisp. So if I type in Pdisp here, everything will come up, which has happened on Pdisp, and you can look through and watch what you feel is relevant, including our GSA raft. So for example, we've got our raft and soil structural interaction webinar, which is available here. Okay, so if I go back into the presentation, please do contact us if you have any queries, and I hope that you've enjoyed the webinar.